Shall we start part 2 of the lecture?
Okay, please.
Okay, so now we finished our talk in the part 1 and we carried out everything, all derivative we carried out with respect to the, remember everything we carried out the derivative with respect to the coordinate of the field point. Okay, in the previous part we obtained the traction Tki of xi and x from u ki of xi and x, and during doing this all derivative are carried out with respect to the coordinate of x alpha of x. Why is that? This is mainly because we compute the displacement at point x. For example, we say uki of xi and x, and this point is x. This displacement is really due to a load at xi, but we compute the displacement at x, and we want to compute the strain Kij at x. Okay, and we want to compute the stress sigma Kij of xi and x at x point. So this is the variable point, but this is always constant. This is always constant. Okay, this is always constant point. Okay, this is very, very, very important. We will change that when we talk later about computing the values of internal points in the direct integral equation. Okay, and this is also the same. This is the same when we carry out the derivative with respect to the coordinate of the field point in the indirect formulation. Because in the indirect formulation, we say for example, ui of x equal to integral of s of xi u ij of x and xi phi of xi, phi j of xi. Okay, here I want to compute ti of x, so the variable here is x, the point x. So also, as we said before, we carry out the derivative with respect to the coordinate of x point to compute the integral equation for x point. Until now, we carry out all our derivative with respect to the coordinate of the x point or the field point. But we have two more cases when we compute values in the direct formulation at internal points. We will change to carry out the derivative with respect to xi. By that time we will say y. And when we use formulation in the indirect formulation for the dipole, we'll use our derivative also with respect to the coordinate of xi, and we'll use y. Remember this in your mind. Now we can start our second part of the lecture. So part 2 of the lecture, we will try to carry out what is called by jump term or C matrix. Sometimes they call it C matrix. What is the jump term of the C matrix? When we differentiate, we will take care about the direct formulation. And for simplicity now, we'll talk about potential problem. If we remember the potential problem in the direct formulation, we used to say integral of gamma of x q asterisk of xi and x, u of x, d gamma of x equal to integral u asterisk of xi and x, q of x, and this is over gamma of x, d gamma of x. This is the direct integral equation when xi is external point. For example, this is a domain, and this is gamma, and here we have x, and we have point xi is external point. But when xi is internal point, we can have the same integral equation, but with a free term here, plus integral of gamma of x, q asterisk of xi and x, u of x, d gamma of x equal to integral over gamma of x, u asterisk of xi and x, q of x, d gamma of x. This is when xi is internal point. Now xi is internal point. Okay, for example, this is gamma, and this is x, and here we have xi, and this is gamma. But what happened when we have xi is a boundary point? This is a big question. When we have xi is a boundary point, I'm going to give you the final answer now, but we will show it now. We will have 1/2 of u of xi plus integral over gamma of x, q asterisk of xi and x, u of x, d gamma of x equal integral over gamma of x, u asterisk of xi and x, q of x, d gamma of x. From where this 1/2 come? And this is when xi is a boundary point. Here we have x and we have xi. Sorry, this is xi, and this is omega, and this is gamma. So when we have point xi is a boundary point, we will have this term, the 1/2. Practically, either this half will appear here, or this half will appear by negative here, and will end up whether from this equation, regular equation, or from the internal point equation here, you will end up to 1/2 when we have xi on a smooth boundary. What is meaning by smooth boundary? What is meaning by smooth boundary? The meaning by smooth boundary is very simple. Is xi is not at corner or any kind of cusp or something like that. It's not a corner point. It is a smooth boundary. Okay? On line, on curve, or something like that. Okay? So when we have xi on a boundary point and a smooth boundary point, this 1/2 appears. This term is called the jump term, or the C matrix. Okay?